In this video, we'll do some practice problems relating to finding critical points and using the first and second derivative tests. So first, let's find the local extrema of a function 3x to the fourth minus 8x cubed minus 18x squared plus 12. Let's remember that local extrema means finding local minimum or local maximums of the function. So what we're going to do is first we need to find the critical points of the function. The reason we have to do this is because we know that all local extrema will occur at critical points. So this will give us a starting point, then we need to test those critical points. So first we're going to find the derivative of the function. That's going to be 12x cubed minus 24x squared minus 36x plus 0. And note that we can write this as 12x times x squared minus 2x minus 3. And we are going to set that equal to 0. When we're factoring x squared minus 2x minus 3, we can factor into x minus 3, x plus 1. And when we set this equal to 0, we get 3 critical points, 0, 3, and negative 1. Note we also need to check when the derivative does not exist, but since this is a polynomial, then we don't have any points like that. We'll see an example of that later on. So we have our 3 critical points. Now we need to test the critical points. Using either the first or second derivative tests. We'll use the second derivative test or first derivative test a little bit later. So right now, let's use the second derivative test. That is, we need to find the second derivative of the function. So I'm going to take the derivative of the first. That's going to be 36x squared minus 48x minus 36. To factor that, I can take out a 12 to begin with. That's going to leave me with 3x squared minus 4x minus 3. And note that that doesn't factor nicely any further than that. So this is going to be our second derivative that we're going to work with. I need to plug in the 3 values, 0, 3, and negative 1, into the second derivative, and then see if the resulting value is positive or negative. In this case, we get a negative 3 inside the parentheses. This is all going to be negative. I don't care what the actual value is, just the sign. Let's do f double prime of 3. That's going to be 3 times 3 squared minus 4 times 3 minus 3. 3 squared is 9. 9 times 3 is 27. 27 minus 12 minus 3 is going to be a positive number. And finally, f double prime of negative 1. 3 negative 1 squared minus 4 negative 1 minus 3. It's going to be 3 plus 4. 7 minus 3 is 4. It's going to be positive as well. So the second derivative test tells us that since the second derivative was negative, then we have a local max at x equals 0. For 3, the second derivative was positive, which means that we have a local min at x equals 3. and same at x equals -1. Note, what is the local max? We could just say that it's going to be f of 0. In this case, that's 12. We could do f of 3. I'll let you figure out what that value is. And same with f of -1. So those are the actual mins and maxes, those values, but they happen at those x coordinates, and that's what we care about the most. All right, let's do another example. Now we say we're going to sketch the graph of f of x equals x to the fourth minus 6x squared. And how we're going to do this is by starting with finding the critical points. We're going to analyze this function by looking at the critical points and the derivatives and the signs of those derivatives. So we're going to find the critical points. That's going to be the derivative 4x cubed minus 12x. We can factor out a 4x out of both terms, and we're left with x squared minus 3. And we're setting that equal to 0. So we get, from this, we get an x equals 0. And from the x squared minus 3, it's like we're setting that equal to 0. We get x squared equals 3. We get x equals positive negative square root of 3. 3 critical points there. We also need to think about when is the derivative not continuous, when does it not exist? And this is a polynomial. There's no issues here. To analyze this function, we're now going to think about finding the critical points of the derivative as well. We need to kind of find the inflection points as well. So to find the inflection points, we're going to find the second derivative, which is going to be 12x squared minus 12. Set that equal to 0. Factor out a 12. And we get x equals positive negative 1 from x squared minus 1. So those aren't necessarily the inflection points, but they're possible inflection points. And what we're going to do now is we're going to do the first derivative test / we're going to check the inflection points. But really, all of this is to help us sketch the graph. And we're going to do that by basically finding the signs of the derivative. So I'm going to start with a number line here associated with f prime, and a number line here associated with f double prime. And I'm going to label the critical points of the function and the derivative. I'm going to start with 0, square root of 3, and negative square root of 3. And then for the second derivative, we have 1 and negative 1. So in each of these regions, for each the derivative and the second derivative, I'm going to test a point. So for the first derivative, there are 4 regions to check. And I need to find points in each of those. And we could pick maybe -2, -1, 1, and 2. Those seem to be nice values to check. So when we're checking this, we are going to plug those points into the derivative. Maybe it's good to factor this out. You don't have to do this. If this looks confusing, don't do this. Might be nice to use that factored version. If not, then we can just put the version that we had. 4 times -2 times -2 squared minus 3. This is going to be a negative number times a 4 minus 3 is a positive number. So overall, this is going to be a negative number. Check the same thing for -1. We're going to have a negative number times -1 squared minus 3 is a negative number. This is negative times negative, which is positive. Check the same thing for 1. 4 times 1, 1 squared minus 3 is going to be positive times negative, which is a negative number. And check 2 as well. Which is going to give us positive and positive, which is a positive number. So at this point, we could actually classify those 3 critical points for the derivative, or for the function. Negative square root of 3 is going to be a minimum, 0 is going to be a maximum, and square root of 3 is going to be a minimum. And we'll see that when we sketch the graph as well. Now let's do the same thing for the second derivative. We're going to test 3 points. How about -2, 0, and 2? We use integers if we can. We have to get fractions if we have to do that. So f double prime of -2 is going to be 12 times -2 squared minus 1, and that's going to be a positive number. So on that entire region, the second derivative is positive. Let's test f double prime of 0. It's going to be 12 times 0 squared minus 1, and that's going to be a negative number. And finally, we'll check f double prime of 2, which is going to be a positive number. So there we have it. We have the signs of the derivative for every single x value. And we're going to use that information to graph the function. So I'm going to go to the next page. We're going to graph it there, and I'm going to put down this information on the next page. So here we have our information. And before we start graphing it, I think we need to find one more thing, and that is maybe finding the X intercepts. It's going to help us graph this very well. So the X intercepts here, we're going to have x to the 4th minus 6x squared. We're going to set this equal to 0, factor out an x squared, and we're left with x squared minus 6. And that's going to be x equals 0 and positive negative square root of 6, which is somewhere in between 2 and 3. So let's label those x intercepts first. We have 0, we have square root of 6, so a little bit before 2.5, and negative 2.5, negative square root of 6. So the function is going to go through those points. We know that it is going to be decreasing to negative square root of 3. Let's label the negative square root of 3 on the graph as well. Note this lines up with that point. So negative square root of 3 and square root of 3. And we should be able to kind of graph everything now. So there's a few different regions here. I'm going to erase this X intercept stuff. So on this first region from negative infinity to negative square root of 3, the function is decreasing and concave up. From negative square root of 3 to negative 1, the function is increasing and concave up. From negative 1 to 0, the function is going to be increasing and concave down. From 0 to 1, we're going to be decreasing and concave down. From 1 to square root of 3, we're going to be decreasing and concave up. And we're going to be increasing and concave up for the rest. So decreasing concave up is going to look like this. Increasing concave up is going to look like this. Increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. And we're just going to kind of put those shapes, connecting the dots in a nice way, going through those points that we need. Note that we have minimums at x equals positive negative square root of 3 and a maximum at x equals 0. And we have inflection points at positive and negative 1, as that's where the second derivative will change signs. So we know that 0 is going to be a maximum. We know it's going to be a minimum at negative square root of 3, positive square root of 3. We have X intercepts labeled there. So let's try to graph this. This is going to look something like this. Let's see if I've done everything correct. From negative infinity to negative square root of 3, I'm decreasing concave up. Negative square root of 3 to negative 1, it's a little bit iffy where that inflection point happens. But let's just say it happens at that point. We go from concave up to concave down. We go from increasing to decreasing at 0, decreasing and change to concave up at 1, and then all the way out. The graph may look a little bit different, but that general shape is what our graph of our function will look like. So there's a lot of information there, and kind of pooling all that information can take some time to get used to. I think if you are struggling with the graphing part of this, just try to graph it a few times. Don't try to do it all in one step. Just try to graph it and then try to fix it as you go. And then once you get a good idea what the shape should look like, then try to graph it if you're struggling with that aspect. We're going to do this one more time. So sketch the graph of f of x equals 2x squared minus 2 over x. First step, we are going to find the derivative, which is going to be 4x minus the derivative of 2 over x, which is going to be plus 2 over x squared. Let's note that the derivative of negative 2 over x is the derivative of negative 2 x to the negative 1, which is decrease the power by 1, decrease power by 1 and bring the power out in front. 2x to the negative 2. So let's set this derivative equal to 0 and solve, find the critical points. I think the best way to do this is to multiply by x squared everywhere. That's going to give us a 4x cubed plus 2 equals 0. That is 4x cubed equals 2. X cubed equals 1/2. X is going to be the cubed root of 1/2. It's going to be about 0.79 or so. So there is a critical point. X equals 0.79 or so. But also note that we finally have an instance where the derivative does not exist at all points. So here, the derivative doesn't exist at x equals 0. So this is also a critical point that we need to look at. All right, let's also find the second derivative and mess with that. So the second derivative, I'm going to do this up here, is going to be 4 minus 4 over x cubed, the derivative of 2x to the negative 2 is negative 4x to the negative 3. We set this equal to 0. First thing we should do is multiply by that x cubed on both sides. We get 4x cubed minus 4 equals 0. It's 4x cubed equals 4. X cubed equals 1. That's going to be x equals 1. So that is not guaranteed to be an inflection point, but when we look at the signs of the derivative, that's going to be a special point that we look at. So we're going to do the same thing that we did before. We're going to look at the derivative and the second derivative. In doing this, I realized I made a little mistake here. Here, I should have 4x cubed equals negative 2. That's x cubed equals negative 1/2. That's going to be negative 0.79. Okay. So plugging or using those points, we have negative 0.79 or so, negative cubed root of 1/2, and 0. And we have one value for the second derivative, 1. So we're going to test 3 points for the first derivative. We'll test maybe negative 1. How about negative 1/2 and 1? And we'll test 2 points for the second derivative. How about 0 and 2? All right, so testing these first derivative points, we have f prime of negative 1 is going to be 4 times negative 1 plus 2 negative 1 squared. That's going to be negative 4 plus 2 is going to be a positive number. Sorry, negative number. Negative 4 plus 2 is a negative number. Then we have f prime of negative 1/2 is going to be 4 times negative 1/2 plus 2 over negative 1/2 squared. It's going to be negative 2 plus 2 over 1/4. And that's going to be a positive number. Let's check f prime of 1. 4 times 1 plus 2 over 1 squared. Everything is positive. this is a positive number. And let's do the same thing for the second derivative. We plug in 0. Can't plug in 0. Sorry, that's actually what we can't do because it doesn't work for the second derivative. We have to pick anything else. The second derivative doesn't exist at 0, so we actually need something on both sides of 0. I forgot that we need to think about when the second derivative doesn't exist as well. So sorry, okay, here we go. We need 3 points again. 1/2, 2, and how about -1? F double prime of -1 is going to be 4 minus 4 over -1 cubed. And that is going to be a positive number. F double prime of 1/2. 4 minus 4 over 1/2 squared. That's going to be 4 minus 4 over 1/4. That's going to be a negative number. And F double prime of 2. All right, F double prime of 2, 4 minus 4 over 2 cubed, which is going to be a positive number. Now let's do the same thing we did before. Let's take this information, put it on the next page, and we'll graph the function from then. So here we go, and again, let's do the X intercepts. We have our function is 2x squared minus 2 over x. Set this equal to 0. We're going to do our same trick we did. We're going to multiply by x on both sides, which gives us 2x cubed minus 2 equals 0. It's 2x cubed equals 2. That's x cubed equals 1. That's going to be x equals 1. So we have an x-intercept at 1. And now let's analyze the function using the signs of the derivative. Note that we know we're going to have a local min at x equals negative cubed root of 1/2, which is about negative 0.79. And we are going to have a inflection point at x equals 1. Why do we not have an inflection point at 0? Because 0 is a special value here because it's actually a vertical asymptote. We have a 0 in the denominator. The derivative doesn't exist at that point. The second derivative doesn't exist at that point. It's not in the domain. The domain of the function is negative infinity to 0, union 0 to infinity, everything but 0. So we have a few regions here. Let's take a look at them. Our first region is going to be decreasing and concave up. Next is going to be increasing and concave up. Then we're going to be increasing and concave down, and increasing and concave up. So note that if we are going to be increasing, approaching the vertical asymptote, or decreasing as we go to negative infinity, and there's no x-intercepts over on that side, we have to be above the x-axis. And there's a local min at negative 0.79. this function is going to look something like it's concave up the whole way through, something like this. It hits the min at that point. It's going to be decreasing and then increasing, approaching the vertical asymptote, going off to positive infinity on the left. Note that if you tried to put that below the x-axis, you would have no way of not crossing the x-axis, which would not work because you only have one x-intercept. On the other side, we go from increasing concave down to increasing concave up. We have to start below the x-axis in order for this to work. Concave down, change to concave up. At 1, that's an inflection point and an x-intercept, and there is a graph of our function. These problems can get very convoluted very quickly. There's lots of information going around. The whole purpose of this section is to be able to understand what the sign of the derivative is telling us, what the sign of the second derivative is telling us, and can we put that information together to maybe draw the graph. We talked about how do we analyze the points. Here we're using the first derivative test to analyze the local min. We have an inflection point by looking at the signs of the second derivative.